So today I want to discuss about sampling distribution. It is a very important distribution because it helps in finding out statistical inferences. Sampling distribution can be based on means or sampling distribution can be based on variances. I give you two examples here which will distinguish the application of sampling distribution by either by means or by variance. For example, if you buy a very expensive mobile or a laptop, then you would be very much concerned about the quality of the product, and you don't want to see any kind of deviation in the quality of the product with respect to what the company is claiming for, because you are paying heavy price and you are buying one item for the use. So in this case, even if the production of the product says that the average quality is what the company is claiming, but you are losing a huge amount. That's why you are not concerned about the mean properties, mean characteristics of the product. For example, iPhone mobile, the battery life, the luminance of the screen, all these kind of things must be very ensured. And that's why you don't want to see any kind of fluctuation or variation. In that case, the comparison of the variability of the sample is important, and variance is very important to be compared with respect to the source property. Source is nothing but the the factory which is producing the items, or the claim which company is making about. So there is a source sample relationship. Source has its own characteristics in terms of mean and variance. Sample has its own characteristics in terms of mean and variance. But ideally, sample should represent the source properties. And that deviation is basically we live through statistical inferences, either by mean or by variance. So in this case, variance is important to be compared. But take another example. If you are buying cement bags in bulk for a multi-story building, so in that case, the variability of the bag is not important. The total quantity purchased is important. And in such situations, the average claim would be work fine. And average claim would be very helpful to know that you are not losing the cost. So these are two simple examples to know where you have to compare the mean of the sample with respect to the source or the variance of the sample with respect to the source variance. Now, that is why we call these statistics as mean and variance plays vital role in statistical inferences. Sometimes mean is important, other times variance is important. So sampling from a distribution of a population. See here, this is a source and a sample. When we see source and a sample, source has its own mean and variance, and sample has its own mean and variance. We generally represent by mu sigma square for the source and x bar s square for the sample. Now ideally x bar should represent mu and s square must represent sigma square, but there is a difference. So this is a kind of sample you take out from the source. Now whatever is the variable, either it is mean or variance or something else or some other transformed variable of mean and samples, mean and variance, because sometimes mean is transformed into z as you have seen earlier, or s square may be transformed into some other variance which we call chi square, you will learn later on. So with respect to that random variable, the function represent random variable is basically the statistics, and the relationship of that statistics with the probability of occurrence is called probability distribution. So your statistics may be mean, your statistics may be either x bar or s square, this representation versus the probability of x bar or versus probability of s square. So these relationship will be called sampling distribution by mean or sampling distribution by variance. So these are basically the probability distributions of a statistics is called sampling distribution, either by means or by variance. X bar, so the relationship of x bar versus x bar is the probability distribution there, and the relationship of s probability of s square versus s square as random variable will be there. But in ideal terms, in calculations, we generally don't use x bar and s square directly. We use the transformed variable, and that transformation is basically sometimes x bar is transformed into t, or sometimes it is transformed into z, sometimes s square is transformed into chi square, or sometimes into f, or there are other functions which may be considered in this way. So this is what the basic sampling probability distribution of a statistic. Now, what are the properties? As we know, the location of the sample is nothing but mean, median, mode. This is the central properties of the, so in case we have a distribution, then there are certain mean properties and certain variability properties. So mean properties are these, variable properties are these. So distribution may be with respect to any of these. This is sampling distribution by means, and that was the sampling distribution by variance. What is sample? Sample is basically a set of observations x1, x2, x3 and so on up to the size of the sample. So this is what we call sample taken from a source. So if sample is taken from the source, what basic properties we can draw from the sample is mean of the sample or variance of the sample. So this is variance and this is mean. So mean is nothing but summation xi over n, and the variance is nothing but xi minus x bar whole square divided by n minus 1. This is called as degrees of freedom. So when we have a distribution, as we have discussed in the previous slide, that distribution, sampling distribution by mean is a distribution with respect to x bar. When we convert a distribution, simple distribution, into a sampling distribution, for example, when we talk about sample, sample has two properties. One is x bar and other is s square. This is a source, suppose. Source having mu and sigma squares properties. If we take out a sample, it will give us x bar, suppose, and s square. If we take out another sample, it will give us x1 bar and s square, s2 square. Now if we take out another sample, it will give us x2 bar, s2 square. If we take sampling distribution by means, suppose in this case of sampling distribution by means, we had a source distribution, for example, assuming that source is a normally distributed. If source is normally distributed, there will be some mean and variance. If we convert, this is nothing but the relationship between fx and x. When we convert this into a new distribution, which we call sampling distribution by means, lot is same, the whole lot is same, but we are taking out some set of values here, some set of values here, some set of values here. So instead of drawing the value x on the graph, if we want to draw x bar on the graph and try to find out the probability of x bar, there will be some kind of distribution, maybe the same shape or maybe the different shape. But what will be the mean of the sample and the variance of the sample in relation to the source properties? For this case, we have to find out the mean of the sample, mean of the sampling distribution, and variance of the sampling distribution. Instead of taking out one item at a time, we are taking out set of items at a time, and average is seen as a outcome. So definitely in this case, your variance, the fluctuation which was totally in the data, the variability or the fluctuation in the data, when we see over here in terms of averages of the set, then it will be reduced. You cannot see the total variability over here. You can see the total variability over here, but here, because you are doing average at a time, then it may not be seen, but the mean will remain the same. So it will be nothing but 1 upon n and mu plus mu plus mu, because every time you have a value over n items. So this will be nothing but mu, but this may not be mu, it will be the variability is reduced by the size of the sample, and that will be sigma square by n, which is seen over here. So we see over here the mean of the sampling distribution will remain mu, and the variance of the sampling distribution will be reduced by n. In that way, we can see the distribution which was basically the source distribution having mean as mu and variance as sigma square. When we convert into a sampling distribution of the same data, then this distribution will have a mean as same, but the variance as sigma square by. So that will be the change will occur if we convert the data into the sampling distribution. Now in this transformation from probability distribution of a random sample, random variable, into probability distribution of mean of a random variable will be different. And in such cases, there is one theorem which is applied, and that is called as central limit theorem. Central limit theorem says that if the source data is normally distributed, or not, then in that case, if we want to transform this x bar into z, previously what we were doing was x was transformed into z, and z was x minus mu upon sigma, but there mu and sigma were the mean and the variance of the distribution. But in this case, we are handling sampling distribution by means. Z will be x bar minus mu upon sigma upon square root of n. Sorry, I made a mistake over here. So mu is, because mu x is bar is mu, and sigma x bar is nothing but sigma upon square root of n. So that will be the change over here, which we can see in terms of this. So central limit theorem says that if the sample size increases, then any sampling distribution by means will be converted into Z distribution. So the shape changes and shape transforms towards the Z distribution. Z distribution is nothing but standard normal distribution. So this is what the transformation comes over here, which we see in this case. So n was 1, but when n is 4 or 5, the shape is changed. When the size of the sample is further increased, it comes over here. Thumb rule is generally when the size is more than or equal to 30, when the n is more than or equal to 30, we say that sampling distribution by means will will conform to the Z distribution, that is nothing but standard normal distribution. So it will take the shape of a standard normal distribution if the size of the sample increases. Now this central limit theorem we can see with the two examples of the two shapes. One shape is, suppose when we draw two items at a time from the source. If source having the same data mu and sigma square, we take out two items at a time. Size is n is 2. Then we will have this shape. If suppose we take a sample of 10 items at a time, the shape may be slightly changed. If suppose we take a sample of size let's have 20, the shape will further change, and when the shape is n is 30 or more, the shape transformed into the shape like Z distribution or standard normal distribution. So whatever is the distribution, that can be handled with the case of a standard normal distribution if the sample size is higher. Take another example. Any shape of the sampling distribution, if the sample size increases, transforms into a standard normal distribution shape or normal distribution shape. That is what we call central limit theorem. And this is what we can say central limit theorem. When n is tending to infinity, the distribution turns out to be towards Z distribution. We take the advantage of sampling distribution by means when the sample size is more. If suppose this is a distribution where the relationship of variance, mean and this, and if we have to transform it, again there is a mistake over here. Here is square root of n. So now when we transform into this, it will become a standard normal distribution. So any problem of sampling distribution by mean where the sample size is large, thumb rule is more than 30, and this thumb rule comes from the tables available of statistical tables which are available where the size is 30 seems to be a sufficient number of data. After that it is difficult to have the data in table, although you can use the softwares to help you. But in this case we say that when the sample size is more than 30, we can handle the sampling distribution by mean with the standard normal distribution. In that case the transformation variable will remain Z, and Z will be handled like this. Z is nothing but x bar minus mu x bar upon sigma x bar, where mu x bar is nothing but mu and sigma x bar is sigma upon square root of n. So that is how we handle the sampling distribution by means. Take an example which we can solve. We can understand with this example how to solve such problems. I read out the problem for you. Traveling between two campuses of a university in a city via shuttle bus takes an average 28 minutes with a standard deviation of 5 minutes. So what they say, they are basically giving you the source properties. They are giving you the source properties where mu is 28 minutes and sigma is 5 minutes. They are not giving sigma square values. In a given week, a bus transported 40 times. So the sample is where the size is 40. What is the probability that the average transport time was average transport time? They are not saying the transport time. In normal distribution problem, we handled what is the transport time. So in normal distribution problem, we were looking for x more than 30 for example. But in this case, it is not the case. In this case, we have to find out the probability that x bar is more than 30. That is what we have to see. So in this case, we have to find out these conditions. Let's come to the solution, how we can solve it. So now in this case, source properties, mu is given as 28, sigma is 5. So what will be the source distribution? You can draw it like this: 5 sigma 5 and this 28 mu. Now because n is large, so you can transform this into sampling distribution that will be similar to normal distribution as per central limit theorem. So based on this we will transform, then z for the sample will be x bar minus mu upon sigma upon square root of n, where x bar is nothing but 30. When it will transform, then what we are looking for is inner distribution of mu as 28 and sigma as 5 upon square root of 40. What is the probability that it will be more than 30? So if this point is 30, then we are looking for this probability that x bar is more than 30. That is what we have to find out. To find out this, we will transform this into z distribution. So z is nothing but 30 minus 28 divided by 5 upon square root of 40. When we calculate this, 2.53. For this value of z, when we transform this into standard normal distribution, mean becomes 0, axis is z, and this point will be z naught, which is nothing but 2.53. So this probability of p z more than 2.53 will be equal to this one. Now this probability we can see from the table of standard normal distribution. So if we go to the table of standard normal distribution and we are looking for the point which is 2.53. So 2.53 is this point, where 0.3 is the 0.3 is what we call the second digit value. So this probability is this one, but this probability 0.9943 is the probability of point z less than or equal to 2.53, 0.9943. So if we come back over here, the probability given in the table is probability of z greater than 2.53 will be nothing but equal to 1 minus probability of z less than 2.53, which is given as 1 minus 0.9943. So that probability will be 0.0057. So this is the probability that the sample will have a mean more than 30. This is how we can solve the problem for sampling distribution by means. So this was the basic starting of sampling distribution by means, where we are using the very common distribution, Gaussian distribution or Z distribution, that is called as standard normal distribution. So we have taken an example, we have solved it. I hope you could have understood. If anything is less, we will be try to clear it in the forthcoming lectures. Next lecture will be based on sampling distribution by mean and variance, which are very common distributions, T and chi-square distribution. But these distributions are applied where sample size is less. Thank you very much. Good luck.